Well, it's been a little bit of a while. Um, I'm still working on the uh, Smalltalk graphics library and drawing program, but it is going very slowly. I've had some kind of changes in my life. Basically, first I had a kidney stone. I was in the hospital for a little while. That was no fun. I don't recommend it. And then also, the company I worked for had been acquired, and so uh, the new owners decided to lay a bunch of people off, and I was one of those people. I am now reevaluating some things in my life, and uh, rather than look for a job right away, I'm working on something. So I'm gonna talk more about that later. But tonight's uh, broadcast has something to do with that, and so what I'm working on tonight is a virtual machine. I've actually built the virtual machine several times. It's something I've been working on for several years, off and on, playing with this idea. It's called the B4 Virtual Machine. It's on Engine Storm B4 on GitHub, and and it's a very small virtual machine. It's kind of modeled on the idea of, well, modeled after the virtual machine that came with RetroForth 10. So RetroForth is a Forth interpreter. It's a really cool little language, and RetroForth has had numerous. It was written originally bootstrapped from x86 assembly, and then um, the current maintainer, Charles Childers. Sorry, Charles, I don't know your name. He goes by CRC online, but he he made this machine called the Ngaro virtual machine, and now he's got, I think, several successor machines that are based on this. But that's where I really learned about Forth, the Forth language. And so ever since then, I've been thinking about making a very, very small virtual machine, very similar. Ngaro had 32 instructions, and I actually wrote a implementation of the Ngaro virtual machine in Pascal, so it's actually in here still. Defender ref, directory UC ref, and then, well, there's just a whole bunch of stuff, a bunch of old experiments in here several years ago. But oh, I'm expecting to see a. Maybe I moved it already. I think I did. I actually did. I was just looking at an old copy of the repository that I had some stray files on it, and I think I moved it to a different. Anyway, it doesn't matter. Maybe I'll show something real quick just to give you a feel for what we're talking about here. So if we go to games.tangentcode.com, Minesweeper, Mineswpr, you get this, which is a retro terminal. So this is RetroForth 10, and I put a JavaScript terminal on top of it. I think I had added the color stuff. It had someone else had already written the virtual machine here. So the idea is that you had the virtual machine written in a bunch of different languages, and then you could put your code on top of it, and that code would run in all those different virtual machines and all those environments. I thought that was a really neat idea. We had this really tiny virtual machine. The spec was really clean and has like 32 instructions. It has a stack. It has a pair of stacks and some RAM, and then an instruction pointer, and that's like the whole machine. And then these 32 instructions, and then from that, you can save the entire state of the machine as an image. And anyway, so that's what you're looking at here. So this is a game of Minesweeper that I made in that language, and so this is actually the RetroForth prompt, and I've modified the prompt to print out the game of Minesweeper. So every time I type a space, we're going to get something. So I want to like say, looks like the command format is the X and the Y directory. So if I say 4, 2, then that will be that spot right there. If I say 4, 2, and you see every time I hit a space, it actually refreshes the screen, and you're looking at the stack here. So this is the two items on the stack are 4 and 2, and then I have to say plus. I have to say yes, it's a flag, or yeah, so flag it, unflag it, or prod for a mine. So I don't know what it is, so I'm going to hit a question mark. When I hit space, then either it's going to blow up or it's going to unveil some of the minefield, right? Okay, so now you're seeing that's next to one mine. So one of those surrounding things is fine. We'll just do another one like over here. So like B8, and it's all like hex, and it does this, and so we'll do it again. We'll just do it until it explodes. And so we'll say, oops. Oh, interesting. I think it's Control H is what is not does the backspace rather than backspace key. We'll do that again. I'll get another one in there. Might be a lot of mines in here. We'll do how about 6? B4, right? I should have done B4, and then we'll do question mark. Go. Okay, that's really super. There you go. Just all kinds of mines over here. 4C question mark. There we go. Okay, so it does a little flood fill. There's actually a bug in here, and I never was ever able to track it down. The code is really fun, and in fact, it's up on Tangent Storm at the moment, github.io. Just to give you a feel of what Retroforth looks like, and Minesweeper here. And you can see the code, very freeform syntax. Basically, it's executing one token at a time. That's a fourth. That's the property of fourth in general. Colon starts a word, so then I'm defining this Unicode character here to be greater than or equal to. So there was already a greater than or equal to, so I'm just redefining it, and that's the end of the semicolon ends the definition. So basically, that defines this symbol to mean this built-in Retroforth word. Hello, whoever just joined in. And so this is the documentation. One of the first things I did when I was working with Retroforth 10 at the time was I built a documentation system that would allow you to, I'm not sure, maybe this was already in there, but basically, this little colon symbol starts building a dictionary in memory. It's all very low level. And I think this was like, I'm not entirely sure. This was like 10 years ago. And anyway, what I did with the docs is I made like an interactive thing where you could actually see the docs. And that might actually be present here. If I go back to Minesweeper game, when we quit, so we hit Q to quit, we'll be back in the Retroforth prompt. And if you see words, it would show you all the words. But this terminal does not scroll, so it actually clears everything. But you can see like it just comes with a massive number of words, and then all of these are new words that I'm defining. And I'm not going to go through this code, but I'm just kind of wanted to give it like a little feel of what kind of language I did. So actually, this is not a Forth style language. These are .if so and else, and that's like my take on what Forth should look like. The Retroforth, Forth is a really old language, but Retroforth actually puts in this idea of combinators, combinators and quotations. So like this right here is a quotation. So it's basically it's not a lambda because lambdas are written a certain way, but it's a different syntax for the same idea as a lambda, an anonymous function. So rather than running flood here directly, it's actually a function that when invoked does flood. And I think flood is the recursive function that does the flood fill. So yeah. Anyway, I'm not going to go through this right now. But the point is that it runs on this. Oh, there you go. So whatever. Here's a case statement. I'm not exactly sure what this is. When do maybe this is something like a case statement. There are no statements, right? Again, you're executing one token at a time, and then some of those do things that allow you to, like, basically the definition of this little colon is a compiler. I'm rambling here. I didn't really mean to ramble. But basically my history with this project was I implemented the virtual machine for this system in Ngaro. I built this terminal here for JavaScript. I think if you say clear, it'll clear the screen. I think if you say help. Yeah, so I made this. This is what I contributed to Retro 11. Oh, Retro 11. Okay. 10. And I think he's on 12 or 14 now, and like he's got a whole new virtual machine, and this is all gone. all the words are different. It's a completely different language basically. Retroforth.org, retroforth.org. But he's definitely up to really good stuff. He's built like this whole web server is all being run on it, and it's well worth checking out. Maybe I'll do a whole talk on Retroforth someday when I get back up to speed, or maybe I'll revive Retro 11. That's the one I learned. I'm not saying it's better than, he's probably improved in a great many ways, but this is the one I'm most familiar with and that I actually have some experience with. But I'm also building, my own Forth, and that kind of inspired me to build something. And I've been kind of playing with it for a while, and that Forth is called B4. And the intent was to write it as a tutorial, right? To write a tutorial. I'm sorry, that's something different. I'll talk about it in a minute. And so I started this project probably, I want to say 10 years ago. And yeah, 10 years ago that's where I put the gitignore file. And, I've every couple years or months, I come in and fiddle with it and do different things. And I actually have a fairly decent idea of what the virtual machine is going to look like. And I've actually implemented 2 versions of it. So one is in J, of course, because everyone, that's the first language someone would go to when you. It's one of the first languages I go to. It's actually a pretty nice looking for a J file. I found it very satisfying to write this. So these are what I call microcode. These are pieces that can compose to build the instructions that I want to do. So like the basic idea is you have a data stack, a return stack, and so then D and R are doing like put something on the stack, on the data stack, put something on the return stack, get the top of the stack, get the next on the stack, swap the things, pop off the stack and return it to J. Same thing. And then B, so fetch a byte, fetch a signed byte, a short. They call that in Pascal. Put a byte, fetch an I32, fetch a store an I30, so a signed 32-bit integer. And then there's this thing called the Skippy bit in the virtual machine, which I completely forgotten about, and it's only in this implementation as far as I can recall. But basically, it's got a bytecode, but it's only using like a handful of the bytes for like built-in operations, and there's precisely the bytes that are not allowed to be used in a UTF-8 encoding. So any valid UTF-8 string just gets parsed as data, and you just know if you're looking at a UTF-8 string, it's data. And if you're looking at a symbol that could not start a UTF-8 string, which is one of the high numbers in in the range 0 to somewhere around like the bottom half of the ASCII plane, right? Like 200 somethings. Those numbers are where the opcodes live. And so that's the basic idea of the virtual machine, is that and then the 32 unprintable characters that are before a space in the ASCII plane. So the bytes 0 through 31, those are registers. They're special symbols that are used to retrieve one of 32 registers and put it on the stack. And those are, maybe I may be saying that wrong. Maybe they because you have to be able to read and write them. I'm not entirely sure. And the idea is that those are reserved for memory locations. Yeah, I'm not sure. I'm not sure what I'm saying. I'm not sure how that works now that I think about it. But no, that's not what happened. What happens is that there are 32 registers in memory, and that when you invoke those, what they do is they dynamically invoke whatever function is pointed to by those registers. So those registers are 32-bit pointers to values inside this array, and it basically causes the instruction pointer to call that function correctly. So those numbers are a dictionary basically. So you have a 32 entry dictionary that you can use in the virtual machine itself, and so you have 2 stacks in a dictionary, and that gives you a Forth. And so that's the idea. So if you saw the previous talk that I did a while back about building a little language, I think it wound up taking 3 episodes um, on this stream. That's a very high level thing, and this is the same concept, but it's all the way down. It's all the way down to the level of assembly language or an assembly language for this virtual machine. So anyway, that's the hardware. That's what the microcode does, and then in J we assemble those hardware pieces into these opcodes operations. So for example, LB loads a byte onto the stack, and so what it does is it puts some data. I guess it increments the instruction pointer. So you're currently looking at the LB instruction. So it increments the pointer. It gets a short signed byte, I see, and then puts it onto the data stack. And so that's the composition of these 3 microcode instructions gives you this. And so it's actually basically meant to be like kind of a mathematical description of what's going on in this language, and kind of a spec for the virtual machine that just happens to be executable. So I'm using J as a specification language. Let's see. So there's all these other instructions. We've got and or and XOR. They all have these 2-character codes. That's just what the assembly language looks like for this. And the idea is that, well, you'll see in a second. Yeah, so here's some assembly language right here. So I think this is saying something like short integer, and then that's the number 1, and then duplicate it and then add it. So this would produce the number 2, and that's why it says assert that as the right. So and the assembler for J actually basically just looks at these opcodes. It sorts the names from above here, or I don't know. There's a list of them somewhere, and this is the UTF-8 handling. Right, and there's a calculator mode, so you can actually use the virtual machine. From remotely, basically. And that's kind of what I guess I kind of lost my train of thought. But, the idea is that this what I want to do right now is expand this little, like I think this is the extent of my test suite right here. So we've got a little assembler here. This is the assembler. Very small thing. And surely there must be something that says like what the opcodes are. Somehow I'm fetching these names. Somehow I have a list of these names. I don't know where they are. I'll have to read the code again. Oh, maybe it's this. So it's this list of operations gives you this, and so these are the ops. And then I guess they're indexed, and this is composed into a list. And so we've got, there's a file called mnemonics in here. Anyway, I'm just kind of like reorienting myself. I haven't looked at this in a couple months, about 10 months it looks like, according to the changelog. So I'm kind of loading this back in my head. There is a second version of this, which is written in Pascal. And they are not in sync. They're both, every time I sit down and write this, I make slightly different decisions about what the opcodes are. In fact, I say there's 2 versions of it. There's 2 good versions of it. There's also this Forthy. This is something like the empty interpreter, high level empty interpreter for JavaScript. I call it empty forth. Here's another version of a different version of an interpreter that used a different set of opcodes, also written in J. Here's a different version. Oh, very small version. Here's a fourth.ijs. Anyway, there's a bunch of little experiments that I put together, and I kind of got like a good system that I really liked. Here's another virtual machine. This is actually not mine. The Niklaus Wirtz one. No, this is a 16 instruction. I just made a bunch of these little virtual machines, and you know, some of them have code implemented on them, and I just made a lot of experiments and stuff. Somewhere in here, there's other versions of this. There's start on something in JavaScript or in Java in processing, which is Java. Try and draw the thing. But the idea is that, you know, this is going to be like a little tiny virtual machine. This is whatever. Little tiny virtual machine, and you use it to implement a toolbox of things. Well, first of all, it's a lesson. It's going to be a set of lessons. And you have it in a bunch of different languages, though, including whichever ones the people who are going through the lessons want to look at. And you can run the same code atop all these different languages. Kind of the idea, like I guess the core idea would be that you're abstracting away the technology stack, right? You know, we make, when we talk about cross-platform code, we're usually talking about, well, the code runs on a Mac and it runs on, you know, Windows and it runs on Linux, and maybe it runs on your mobile device or whatever. So getting code to run on different computers is easy, and that's because we've abstracted away those differences between the hardware, but we have these different platforms atop the hardware. So you have, you know, the Python runtime, and you have the web browser, and you have, you know, working inside of a terminal versus working in a GUI, and you have all these different options, and sometimes those options force, you know, or at least a strong influence on what, you know, technology stack you want to use for a particular project. And if you're locked into something, you know, basically you have to make the decision, well, do I want to be locked into this forever, meaning that I'm going to stick with this one area? And for me, that was a mode. Like, I started writing some code in Python. I had all these Python libraries that I was fluent in, and so it's like I didn't, you know, I would go play with other languages, but I didn't really want to get away from Python because I was so good at Python that I wanted to do everything in Python. And so in a way, I was locked in. But then I would try all these other languages, and I was like, man, I wish I could do this because I've been exposed to this idea. I wish I had that in Python, but I don't. You know, and I wish Python would run in a web browser, and it, you know, maybe it does today, but it, you know, it didn't at the time. And anyway, the idea was that this would be like kind of a little Centaur thing. So you would have the runtime, the virtual machine implementation in your different languages would become the new platform that was now standard. So you'd have a standardized platform sandwich, right? So just as we standardized the hardware with POSIX and you know Bash, and you can run the same commands everywhere. So now you would have on top of the language a layer that would do these things, and then you would be able to treat the language the way the way you would treat the hardware of these different machines. Like, why would you use a different machine in the first place? Well, because you had the machine, but also because you might want to get access to something that particular machine does. And so now the idea is, well, you put your toolbox into the V4 virtual machine, and you can have the same. Like, you don't have to learn a new parsing library just because you change languages, right? You implement this one thing, and now you got all the tools that you can take with you however you go, into whatever language you go, and you don't have to worry about porting every tool that you want to use or learning a new tool. You always have the choice, right? You don't, and that gives you a lot less lock-in and a lot more flexibility when it comes to making the choice about what technology. You can even postpone the choice for it, definitely. That's the idea. And then, but also, I wanted to, ever since the idea occurred to me, like, I've been wanting to teach to make this be a course where you learned. So it starts with that virtual machine, and in a minute I'll show you the. Hang on a second. Interest right now. Or if I go into the past directory, You can see on the left there, this is the BIOS written in the B4 assembly language. It's many pages, several pages, not too many pages. If you say B4, then you get this fourth flag shell on top of it. This is the Pascal version. This on the left is B4 assembly language, the Pascal version. B4. Actually, some way there's a way to see like a. Okay, so you say bye. Oh. You don't have a backspace at all there, but B4/D. There you go. Now you get the debugger. And so that's this highlighted thing is the instruction pointer. And I don't know what it's going to do, but oh, no, actually, it's not incrementing it. What do we do? We have to. That's just moving a cursor around. So yeah, so they're both on the same square, so it turns purple. Otherwise, it's blue and red. This would increment. What's the EP? I don't know what EP. Oh, that is. Sorry, you say C to continue. Anyway, you can run through it and it's a debugger. And you can see it's printing out the words. That's the initial thing that it does. Like in green here, it's actually showing you the definite, like here you can see it's printing out put S, or it's calling put S. So even though there's no, you actually do have a stack here. This is the stack, but you can't really interpret what it is. You know that it's on the, you can't see what the name of the function is there. But C, right? Yeah. I think TW means write to terminal or something like that. And I had some mnemonics. It's been a while. So ideally, you would have like space on the screen to see what. Oh, here you'd be able to see what exactly every one of these things is doing, and Anyway, so if I just say R to run, there we go. It just runs as fast as it can. And is there a word called DB? No. Somehow there's a way to restart that debugger. I forget how. We'll see. No. Full space. Yeah, if you type words again, you get all the words. Yeah. I don't really. I'd have to look at that. I'd have to study the language a little bit more. I kind of got things working. So this thing has a. So you're looking here at the code for the Pascal version, which kind of leapfrogged the J version a little bit because it has this terminal interaction. I think at the time that I wrote this, I either didn't have JKVM or I hadn't hooked this up to JKVM. No, that doesn't make any sense. I'm not sure. No, what it was is I'd done this years ago in Turbo Pascal. Long after Turbo Pascal was obsolete, I fired up DOSBox one day, an hour worth. Not an hour, whole night making a little tiny version of this, and then I now use Free Pascal, modern operating system. And I A, brought it closer in line with the J version, and B, just added all this fun terminal. I think it had a debugger to begin. It has a. Okay, I'm rambling. Let's see. The point of this video is that I have these two versions. They're not in sync. I'd like to get them in sync. And one of the things we did I helped contribute to Retro was a test framework. I wonder if I go to Tangent Storm. I have Retroforth. Tyler. I also made a implementation of PL0 in that. Repository. Oh, Retro. Okay, yes, Retro, just Retro. Actually, don't know. It's in that repository. Yeah. So 10 years ago, this is my code from. I think I used a Git to break this out of some Git subtree command to break this out. Or maybe this is actually just Retro. Yeah. Right, because he didn't use GitHub. All right. Well, anyway. Test. I was saying test. And here there is a Ngaro. I made the test for this. What did I write for this? The external test suite for Ngaro implementations. Because part of the idea was this machine was all specced out, and so anybody could just go and implement it, like I implemented a Pascal version. And so it was possible that the implementations were not in sync, or even if they weren't in sync, just I was writing tests for it because I wanted to write my implementation, I think. So I wrote this weird looking Python, but that's how I write Python. Unnecessary line breaks and things. And yeah, let's see. Yeah, so we're testing each one of those little things. It looks like we build a whole image. Like the layout of memory is stored in a file called an image file. And then we're going to run the assembly language, and then we'll see what the result is. So these could probably be much simpler. So what I want to write is a test suite that does this, but probably something a little more data driven. We have a string of assembly language instructions in what am I trying to say? In the sorry, right at the moment. In D4 assembly language. And so you'll have a string of that, and then you'll say, what do you expect the data to look like, and what do you expect the address stack to look like for each combination of these inputs. I think we could probably make a table. Like these are all very regular. So you have a string, and then you have a input and an output, and so on. So this could all be stuck into a big table, and then generate the test cases. But okay. So then the very last thing I want to ramble about for a little bit is LearnTrist. So style of test cases that I want to do, in addition to just actually testing all of the operations, what this does, providing at least some example of each one, is I wanted to make it kind of a narrative set of tests. So we have this idea called LearnTrist. Yeah, LearnTrist. And it's I started this with a friend of mine, and I wrote most of the tests. The tests are written as a kind of story. So very first test is this: establish a command loop and a way to exit. So you're we're going to send the input queue to your program. Test runner is going to connect to your program over some channel, usually standard input. And the name of the test is this, you quit, and this is text that is presented to the user. And so the idea is that you creating a trail of tests that somebody has to follow. And I'm probably going to make a whole video about LearnTrist at some point. Not a rambling video like this. I'm as I said, I'm about to have some free time to make a lot of videos, and I'm going to spend that time on videos that are scripted. This channel, if you can't tell, is just me rambling, whatever comes to mind, but trying to get the words onto the thing and go through the practice of talking something out, and or working on something that I'm not going to bother explaining in detail right now. I'm going to explain it, and if you want to see like the details of how something got built. So people watching this in the future, I hope there will be a thriving community of people who are running the future version of this test runner, and you'll be able to see, oh, this is what, hey, that LearnTrist thing is now up on the web and has a nice fancy graphical user interface and on a web page. This is where it came from. It probably will not be written in Python at the time. Probably be written in Flutter. Dart. That's an example of wanting to have the same code in different platforms. I want what Flutter provides, so I've got to port the whole logic. I said you have to. Anyway, so yeah, so then the next thing you do, the next command you give it is, well, you're going to print the what Tetris calls the matrix, and so this should be the output. Anything with a hash mark is ignored, and even at the end here. But this output, all these little dots should be the output of the P command. So you're printing an empty well because it's the start of the game, and then you queue and then you quit. So if this test fails, actually right now, regardless of whether the test fails or run, when this test runs, it prints out. It runs your program, gives you this, and checks for this, and prints out this, and then if the thing it's checking for isn't what the output was, then it prints this out, and it just goes through the tests in order like that. So that's it just runs through a whole sequence of tests, and then the idea is you design the tests in such a way that they are small bite-sized challenges. So like this is after you start an empty program and all it does is quit. So then the next easiest thing to do would be to print out the state of the game, the screen, and you just print it out with a bunch of dots because there's nothing on the screen yet, empty screen. So now we're gonna, we want to set up some test cases. So we want to give you some blocks on the screen. So these are pixel colors in the traditional Tetris pixel colors. So you say, I'm going to give you some input, and you can ignore this, but these are empty. These are magenta. These are blue. These are cyan. These are green. These are yellow. These are orange. These are red. Here's a cyan block coming down. Here's you can see a magenta T. Here's like a red Z. Here's looks like what's left of a J or an L, whatever the orange one is. Here's a green ZAG. I guess that's the S, and then the R is the Z. Here's O, another orange bit. Here's some blue that's been left over. I don't know who would have gotten in that position by dropping it. Here's the yellow block, 4x4 square. And you can see we're sliding the cyan block down into the bottom here. And so then you load that into your game, and then it asks you to print out the state, and so it prints out exactly what you just gave it. So the G command instructs LearnTrist to read 22 lines of text from the standard input stream. Use the characters on these lines to populate some internal representation of the matrix given, right? It stands for, and here's the color. And so yeah, so this kind of thing kind of builds up a story. it doesn't really sound like a story at first, but it actually has like narrative components later in the game. It's not very even. Right? As I went on, I started like adding characters, just like, oh, your buddy from the other team or whatever, marketing or whatever, wants something changed. Then you can ask for like the score, and so you're basically, it's just walking you through getting a protocol with all the default values. And we're going to do the same thing. Bottom line of all this is that I want to take the same idea, I want to take the same test runner and do the same thing before the before virtual machine. So in a way, LearnTrist, the thing you write is in the LearnTrist game is a virtual machine for playing Tetris, and this is a virtual machine for general purpose virtual machine. I really like this style. Like, I think if we go to LearnTrist, the actual thing is forked from Learn Programming LearnTrist, and it's like 224 people have started, 273 people have forked it. So that's, I don't know how much overlap that is there, but it's about 400 people or so have used this, and all it is just like terminal. It's a test suite, right? It's a terminal suite, and we were pushing it on the IRC channel on Freenode at the time. Freenode is now, it was purchased by somebody, and then everybody left and started a new thing, and then the Learn Programming channel is still there on the new one, Libera chat. But hasn't really, not nearly as active as it was. The people that were working on this are all gone a little bit. Including me. I didn't have a full-time job when I was actually working. I'm back in that. And at the time, so this was all of these things. You can see it like 10 years ago. It was all about the same kind of time in my life where I was thinking about making a course. I was, I was working with a lot of people, doing a lot of mentoring in IRC, and really thinking about what I wanted to build. And I came up with this idea for a course, and I started on it. Surely it wasn't 10 years ago. Like, I was around for a couple of years, probably 2 or 3 years, working on this course as like a side thing. I did have, I say I wasn't employed, but I did have a small business. I was running a web hosting company, but I wasn't actively programming full time. I was kind of like brainstorming and learning a lot of stuff that was going to go into this game. Well, I was kind of, I don't know. It was a weird time in my life. I was trying to brainstorm something and work through a lot of problems and come to an answer on things, and wound up spending a lot of time and not shipping something. So I had a lot of unconstrained creative time, and that's not a good recipe for shipping something. And I ran out of time, and I had to go get a job, and so I went to a job I didn't like, and then I got a job at the company that I work for now, and still work for. And however, and I've been there maybe almost 8 years now. But as I said, we got acquired, and they laid me off, and just for whatever reason, they people they laid off, they told us you're laid off, and then keep coming in for another couple weeks or whatever. So I have the last couple weeks of the year here to think about what I'm going to do next. I have a couple paychecks, which is nice of them, and I guess it benefits them because some amount of knowledge transfer going on. So now I'm coming back to where I was all these years ago, and like dusting this off and saying, this is what I would have done if I hadn't gone to work at this company or companies that I work for. If I had had more time. Now I'm coming back. I have money. I have some savings in the bank. Not a lot of money, but enough to spend some time and really make this happen. And I've also, I think, matured a little bit in. If you're watching this, I can't convince you that I have a linear path from from idea to goal, from goal to execution. As you see, I'm rambling and changing the subject, but I have a general idea where I'm going, and with the help of some to-do lists and some external reminders of what I'm working on, not only can I write what I want to write and build what I want to build, but I can also convey it. I think. Long story short, this is going to be a programming course. This is a programming course. It is in progress. It's been in progress for 10 years, but now it's like, was on the back burner of the back burner of the back burner. Now it makes any sense. And now this is my thing. This is the time to do. Okay, so that was a lot of rambling. I was gonna say, well, maybe it's time to go work on this, but maybe that's I don't know. Sometimes I start up these videos on a new topic, and it's like, well, I spend 45 minutes of me just talking. I don't know if anyone finds this useful at all. It's helpful because now I've loaded it back into my head. I've kind of looked at everything. I've talked it through, and just let me look at the virtual machine. There's a lot of stuff in this repository that's junk, and my plan is to continue cleaning this out. If you came here to actually like see the testing part, then I think that it's way past time where I could have started that or I should have started that talk. What am I trying to say? Well, I'm trying to say that I'm going to make a LearnTris inspired test suite. Oh. But for B4. And maybe what I do, okay, so let's see, do I have all those things in here? CD for retro? No, I don't. Git clone, git at github.com, and storm retro. This is not my code. Source code I forked. It should be in tangent fork. You say make. Oh, because you gotta say CD retro. You say make. You say retro. Oh, it doesn't have my stuff. Right, because it's not my fork. It's not my fork. Right? Where is it? Well, I don't know. LSVM. Let's just say find type VM. I say find VM type. All right, so then these are all like there's a Python one with sockets. There's a C# version. There are all these different implementations of these of this virtual machine. Somebody wrote it in Go. Somebody wrote it in Lisp, HTML5, and so on. Anyway, we say retro. You say words. That's not something. You can say hi. You would say I think the tokenizer lets you say this, hello world. And then put S. S. And then you say hi. Yeah, hello world. And if you you can't do up. But if you write that same thing again, and you say CR at the end, that gives you a carriage return. You say hi now, and it gives you that. I guess you want it at the beginning though. No, we just say hi. Hi, CR, hello world, put S. Yeah, it's kind of weird because the idea is that it's the fourth, so you one token at a time, and so you put things on the stack, and then you call the function you want to call. Say 2 plus. Every time I hit a space, it immediately executes the token I just. I think you say .s, it shows you 4, so that's showing you the stack. say 59 or 582, and we say .s. Here it is. Say swap. I don't know why I'm showing this. This is port. Maybe I should show the. Oh, I can't show it in Pascal because I haven't done it that far, or in B4. The B4 is not that advanced. It can't do a calculator. Or maybe the J version can. But the Pascal version, say make run, I think. Yeah, it doesn't have. First of all, I think. Oh yeah, it does print 5.5. There's no plus. Say ink, and then put S. Put in. Put in. I don't know why two things leaked onto the stack there. Which indicates a need for testing, right? But in theory, the nice thing about the Pascal version of it is it has this BIOS, and figured I guess that could. So what it's doing, so it has there are two assemblers, right? V4 and then V3. I didn't mention this yet. I just changed topics. But so there's an assembler written in Python, but the intent of this is it's a bootstrap assembler, and this is a stripped down version of the assembler. That the intent is that I can write it in itself. So this is enough of the assembler. I call it B3 because it's not the full B4 implementation, but it has just enough ops to be to write it itself. And so what this file, actually it's not this file, is it? It's b3a.org. And so in this literate file, in this org file, I define like all these little structures, and I build out the bootstrap assembler. So here's the bootstrap assembler. These are the ops. These are the ones that I've seen in the code. So the idea is that the output of this program is a Python program that reads the source code for the assembler and assembles it. And then that assembler, the output is now a B4 program, or sorry, a B4 executable that if it ran, it would be able to parse its own source code and produce itself, and it would produce an exact copy of itself from a source. It's a self-compiling situation. And the Python version is just to bootstrap, but because of the way I wrote it, why bother bootstrapping, blah, 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 blah. There's a famous talk, or a famous article, and it's called, it's probably listed in the name here. A guy's name is Evans or something. Bibliography. Edmund Grimley Evans, bootstrapping a simple compiler for now. He does this for x86, but it's like an old version of x86, so like you can't really follow along quite well. So I wanted to do something where you had a virtual machine that was particularly good. If you're going to target some arbitrary virtual machine, why not just implement the virtual machine? And now you got this thing, and now let's bootstrap and just write an assembler. And so we're using Python here as a thinking tool to figure out what the assemblers would have to look like. And so basically, what's the bootstrapping part of it say? Oh, I made some little macros for like dealing with if and swap and all of these things. There's some things that happen. Yeah, so the assembler actually has macros, and the way it has macros is because the virtual machine has this little dictionary in it. So the first 32 operations are, in the bytecode, the first 32 bytes our dictionary. So the operation number 5 like says what's in register 5, do that function. And register 5 is like a pointer to somewhere. Basically, it jumps to whatever's in register. Jump to the address in level 5. Brown Shudaka, hello. I hope I said your name right. Yeah, so I'm making this thing. I'm just rambling here. I don't know if there's going to be a lot of programming here. I intended to write some code, but it seems like I'm just walking down memory lane and trying to load all this back in my head. So implementation protocol from I'm pretty sure that I did this all in my head. Like I don't think I've ever actually run this code. I've run the Python code. But I don't know that I've ever run the resulting code on a real machine or on a real virtual machine. But the idea is somewhere in here we're gonna actually get to actual code here. Let's step through it. So why do this? Blah blah blah. I'm not even gonna read this now. Goals. I want to bootstrap a small REPL. Yep. Which I've done with the BIOS here. Something that's easy to follow and easy to present. Blah 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 blah. This was probably written before it was done because this is about macros used. There we go. So the 32. If you look at what do you call it? The ASCII control codes. Right? Those 32 characters map to the alphabet. Those first 32 bytes. So like nope. Maybe this one. Well, it doesn't matter. Like 13. Oh yeah, see here it is. Control K. Like Control I is the tab key. Right? And if you hit Control I, you hold down the Control key. This little symbol right here, this upward caret, is indicating of the Control key. And you hit Control I, the keyboard will actually send the exact same code that you would get if you hit the tab. At least old keyboards would do it. Like modern keyboards can distinguish it between the two. But like if you ask it for, there's actually two different things that it can send. One is like the actual key code, like what is the physical key that you pressed, and like you hit the Control key and you hit I, and then it has a control flag or whatever. And then there's like I don't know the difference between, I don't know what the two names of these things are, but I think one is usually called like a key code and a scan code or something. But the anyway, the point is that when you hit Control I, it actually does what the tab does. So that's the normal horizontal tab. Control H is backspace, and that's why I think in the Minesweeper implementation here, you had 333 or 5, whatever. You actually hit Control H and it does backspace. Anyway, and so they're mapped to the numbers or to the letters. So the null character is Control 2 or Control Shift 2 for this. Mark the end of a string. Intended to be a null character. That's called null. And then if you hit Control A, you'll get ASCII code number 1, and it looks like it's printed as Control A, but it doesn't mean anything. It means something. It means start of header, start of header, start of text, end of text, and I don't remember. They have like end of transmission, end of text. Yeah. Control 7 was a bell. It actually Control G is a bell, and it actually like causes a bell to ring on your printer or whatever. Line feed, vertical tab, form feed. I use quite a bit. Actually, this file right here. This one, the assembler one. Yes. So if you see, I'm using a key to page between different pages rather than scrolling. There's no scrolling here. You get to the bottom, that's the end of the page. And that's because I have this Control L character, which is the form feed. Most languages support that, and you can. I actually have a VS Code extension that allows you to use VS Code the same way that I have Emacs using, so you can page between your code. Okay. Anyway, rambling. What am I trying to say? I guess I was mostly rambling. Yeah. So. Oh, I wanted to say what was in here. So, I have not actually. Oh, I bet you can say. No, you can't, right? Because the interpreter that you're dealing with in B4 over here doesn't understand these blue words. These are the assembly language, and the assembler, I guess, is what I was leading up to earlier. I'm gonna have to go back and watch this video, and I'm gonna see all the things I talked about, and I'm gonna organize them into a thing, you know, like into coherent threads, and untangle all this. That's what needs to happen. So this is a rehearsal, I guess. But you can see, like, basically every in this assembler we have like a real tokenizer, and it can see, well, okay, if you see this character, ignore everything to the end of the line. But this B3A, the code here, actually it does have that. It does have comments. Other than that, everything is exactly 2 characters. And this is the entire assembler. It's only 85 lines. Is there a version of it that's no? This is the final hex version of it. You can see it's got like an alphabet in there. And here, this is that. Put those side by side. B3A. And we'll have to say hex dump of B3A 0.apt. XD. B3A. Oh, because I'm in the wrong class. I don't have it. B4 B3A. So you can see there's this like alphabet in here, and what these are, these are the first and last characters of all the mnemonics alphabetized, and so there's some algorithm that was, to me, was it's a weird algorithm, but it was good enough to do the string compare to look up the symbol that you want to compile, like the symbol for the, like, say if you want to compile du, which duplicates something, it looks through this list until it finds a D, and it says, okay, now I'm at a D. So now while I'm looking at D's, look through the corresponding next letter and see if it's a U or whatever. So rather than having lists of strings for all 2 whatever. Because I could have done it that way too, but and just added 2 each time. So this says, this is .I is a macro. It says if, which does nothing, duplicate the thing on the stack, load a binary of, load the byte, which is a quoted quote mark, and then test whether it's equal to if the top 2 things are equal. If they are, then .t is then, and that actually does something. That's a macro that does something. I think what it does is it, every time it encounters one of these things, it writes, the assembler writes a byte to like a buffer, and then T says, okay, remember where I am in the buffer, because if it's true, then we're going to fall through and do whatever RYLB to load a byte 0 and return. But if it's false, then we have to jump over this. So remember where we are, emit these bytes, and then when we get to .z, then we're going to go back to this point and fill in the new position. So we're going to emit, remember where we were, emit, and I think you write a space here. You write a jump instruction with an empty slot here, or jump forward instruction with like an empty I think that takes like a byte relative jump, short jump. And so you can jump over up to like 250 instructions. And then and then here you say, okay, here's where I'm going to jump to. So now at runtime, at assembly time, pop this off the stack, go back over here, and fill in the jump, and then keep going. So .i is just so that it looks like an if then, and z means end. There's also a .e for else somewhere, like up here, whatever that is. Yeah. So bw is a command. It's kind of silly, but it says begin word, and we're going to define a word, and basically this turns on what's called the sleepy bit. So what it does is it reads this, and assigns register I, whatever letter, whatever position I is in the alphabet, it assigns the corresponding value. So A, B, C, D, E, F, G, H, I. So that looks like a 9. Right. So slot 9 in RAM, address 9 in RAM is going to be populated with this value. And then when it encounters the word go, so what basically it turns on the sleep, BW turns on what's called the sleepy bit, and it ignores everything else until it sees the word go. That's all it does. That's the purpose of the sleepy bit, is to populate this. I don't remember exactly how the I and T and EZ work. Somehow this is telling it what to do. And so at runtime, so basically the assembler populates this dictionary of one letter codes. So you have like 32 dynamic codes that you can run. Actually, I think it's like 31 or something. It's like the 0 does like always a no op or something, I think. And so basically as the assembler is, as the virtual machine is running this assembly code, this byte code, it dynamically reassigns the I register and sets it to this address in the code that it's emitting, or I don't know. I'm not exactly sure how that works. I think it happens at runtime. As the assembler, after it's been assembled, when it's being run, the assembler is going to dynamically populate those registers with the address of these things, and it's going to skip over these instructions. That was the idea. It's kind of weird to waste an opcode on that, but I don't know. That's how it is in this version of it. And so that way, I didn't have to use labels, right? And I don't know, because this might be the only program that ever uses this. So maybe it's not valid, or maybe I use it as a marker so that a debugger can go back and say, well, okay, this is the start of a function or something. I don't know. So these are basically just informational opcodes that say this is delimiting a function. That's kind of the idea. Anyway, so these are instructions. So the insert, or sorry, the if I is for if, it does nothing, if then else. Then this basically I'd have to look at the org file to see what's doing. I mean, I load a byte, H0 hops over the byte. No, hop if it's 0. Yeah, so hop this number of bytes if it's 0. I don't know. I'm not entirely sure. I think this is like a quote, right? Because it's loading a byte, but the byte it's loading is the instruction H0. And then we're going to write it to the buffer, Z write. So Z is one of the registers, and you write it to Z. So Z is special in that you can write to it. Then load the byte 0, write that, and then copy the Z register, which is the output register. So like the pointer to where you're writing, copy that to the data stack. ZD is copied to the data stack, and then return. All right, so when you do this now, you will have written this H0 and 00 to the output that you're generating, and then you will have a pointer to that 0, or to the space after that 0 on the data stack in the assembler. As the assembler is running, it is pushed something onto the data stack. It's pushed the address here. Then when it hits the well, ignore the else for now. So when it hits the end, it takes that number on the data stack, duplicates it, swaps it with, or copies the end position from the buffer. So copies Z to data again. Swaps those two things. So now you have the position, the end, the start position, the end position, and the start position again because you duplicated it on the stack. And you subtract it. Oh, and then that tells you how many bytes you need to jump. So you're going to write that byte. It should be Z write. No, that's right. It's not Z write because you're not writing where the Z buffer Z is pointing at the end. So that's what Z to the data stack is saying. So copy the end pointer here, and now write a byte at the previous address. So check the distance to the previous address. Now you have a distance, and then write it to that address, so it tells you how far to jump. So this is yeah. So basically, at runtime, this is what you need to do to compile an if then else statement, and then the else is the same kind of thing. I think this looks like it might be like a quoting kind of thing. So maybe I'm not sure what the difference is between these two things. This might be a syntax I developed so that you could write hop 0 same way. This is an unconditional hop. H0 is hop if 0, and if the thing on the top of the stack is 0, the data stack is 0. I'm rambling. Like when I explain this, I'm going to explain this very well, and I'm going to I tried to leave a note to myself. I'm not reading it now, but I tried to read a note to myself so that I could explain all this to students in the future. And so anyway, the point of this is that everything that's not a comment here, comments get stripped out, white space gets stripped out, and then everything else, if it has this tick in front of it, or this caret thing in front of it, that means it's a control code, and you're defining one of the control codes. I'm not entirely sure why that. Anyway, dot invokes it. So here we're defining what W does, and here we're invoking W. So here is the definition, and here is the execution. Yeah. It may be that whenever you see this, it says it's just the name of a register, and it's putting whatever's in that register on the stack, and then the dot in the assembler says, okay, I'm going to choose to use that as a dictionary full of one function call for every letter of the alphabet, and so .w means execute, at runtime, push this onto the stack and then run, and then push the address of this function, this definition, onto the stack, and then run that. So I guess something like that. That might be a little. I guess the thought was that now you can have some very compact code because you don't have to look up functions at runtime. You can just refer to them by these dot values or whatever, by these one character codes. And so the virtual machine for defining lots of similar virtual machines. This one happens to be set up as an assembler. All right, so you've customized it to be an assembler. Now your 32 bytes work as an assembler or work as macros for. I guess I should say, like, the letter A is an opcode, right? And what it does is it. I think that's why that's why there's no. That's why you can't. The letter A is an opcode, and what it does is it pushes the letter A onto the stack, character 65 or whatever, and then runs opcode 0, which is the address of a function that will handle a single character. And likewise, all of the I guess what it actually does is it pushes the letter A could be part of a multi-byte sequence because it's in UTF-8 you have like these escape codes that say, instead of using the letter A, what we really mean is this other thing that's in the same position as the letter A, but on this other plane of the the Unicode chief of stack of objects. Very rambly. This is a terrible explanation. But I don't know. Sometimes, whatever. I don't care about making this channel watchable. Sorry. This is me talking it out. If you want to watch. My other channel, that's where you want to subscribe to. Tangent Storm. Because everything that goes on there, it put a lot of work into. This is. All right. Anyway, so we have this assembly language. Everything is 2 characters. Come back over here. And eventually, so we're going to use that assembler now to write a real assembler. But in the meantime, in the course, in the meantime, I've just written that assembler in Pascal, which is also a very easy operation. Choose to do it that way as well. Just do both, whatever. But even that assembler does not have strings. And so if you want to write a string, you can always use a 2-character code. So here, whatever. I'm just going to pretend we're in in B3 in the B3 language, which B4 is a superset of B3. So or B3 is a subset of B4. And so now you say quote, that actually just says, well, whatever, put that byte there. Emit that byte into the string you're assembling. And then the colon allows you to keep a list of names at runtime, so a runtime dictionary. And so here we're here. So here pointer, that's what that is meant to say, is actually defining that does not compile to, that does not assemble to anything. That does something to the assembler and creates a dictionary associating the word here with the caret at the end of it, the here pointer, to this spot in the output. So .I probably omitted a couple of characters. I'll be, hey sweetie, I'll be done in a few minutes, okay? I'll be done in a minute. LB emits a byte, this emits a byte, and then emits a byte. Actually, I is nothing. So this is a byte, and then this is the string of bytes that were in the assembler. We just saw a minute ago. And this associates that position. This outputs 4 bytes. And those 4 bytes are an integer that can be loaded with the load integer, right? So there's load byte and then there's load of 32-bit integer. And then, so it's actually the start of a linked list. This is a null pointer at the start of a linked list. And we say, okay, there's a linked list is meant to be a list of strings. The first, hello, The first one is 4 bytes string, and it has HERE. These are the 4 bytes. Then here's the actual definition. And so what this is doing is it's basically preparing a data structure for the BIOS itself to use. The BIOS has the BIOS is a fourth interpreter, and that fourth interpreter contains this linked list, but we don't have words to automatically create the linked list, and so instead we're leaving the fields of the linked list in memory. So you can see that we define this pointer specifically so that the next word in the dictionary, so the first word in the dictionary is here. This is the definition of the word. So in the so pass, and we say B4, and then we say here, and we put N. There's no, yeah, put N. Oh, here, put N. So that's where here was. So there were 12 bytes being used up by something, for some reason. By this. The word here, okay, which is the first word in the dictionary. Okay, so what happened when you type the word words is it knows what the dictionary is. Hang on. Here. Yes, this is coming back. So here is a pointer to wherever we have the assembler, and then we have the fourth language, and the fourth language is also assembling things at runtime. So this thing right here, I believe, I don't think I haven't actually written colon yet. Yeah, I haven't implemented yet. But the idea is that there will be a word called colon that reads a word of input and then creates an entry in memory like this. So basically, we're writing the start of a data structure that's going to exist at runtime. That's, over here when this is assembled, we're writing this linked list, and you can see that the next word is last, but it needs to have a pointer to this little header here. In addition to the word last, we need a pointer to this header, and then at runtime we need to tell the BIOS that the name of the thing is last. So you can see here last, and you can see that the pointer to the word here, basically this is emitting the number 12, but as 4 bytes, right? And so it's a 32-bit integer pointing at this, and it's actually, I think, little endian, so the order is different. So it'd be 12 0 0 0 0. And then this does not have a name. So this AP, what is AP? It loads the byte 20. I don't know what AP stands for. But this is not exposed in the linked list. Here we have inc, and it has one of these pointers. This is not syntax. The colon is the syntax. This is just a name. And the $sign, so the colon defines a position, associates the name with the position. The $sign emits the value of that name. And so here we define here pointer, and then here we write here pointer as a 32-bit integer in the output buffer. I don't know what AP is. And then here we say increment, and we're going to define the word inc. And so you can see that this is a linked list, and the very last word we define way down below is going to be called free, and then the entry before that is alloc, allocate, put n, put number. Is this a word? Question mark. Are these two strings equal? I think that would have a question mark after it. Execute words, name. I don't know what that means. Put s, put a string. By x is the interpreter. Comma is the fourth word to write, to assemble something, to like take a number off the stack and assemble it, and write it to output. Um, dec and inc are these two words right here, that increment and decrement, and then last is the pointer that tracks where the end of the dictionary is. No, sorry. Here is the pointer where that's pointing to the last thing that you've written into RAM. That's the last that's the next spot that you will write into as Forth is compiling things and putting data into RAM. Last is the address of the last header. So at runtime, oh, I see. And then as it happens, the way this is defined is that value a little confused. We should have left some registers here. A little bit confused, but it's loading byte 16. So it actually loads the number 16. All last does is put the number 16 on the stack. Say last, and then you say put in, and say 16. So at whatever's that, I don't yet have a way to read and write values. That's usually the @ sign and the exclamation point. At reads and exclamation points and forth. And so, but in any case, I'm not entirely sure why it says the number 16 there. I'll have to think about that because this should be like the first slot in memory, and then here, I'm not really entirely sure. But whatever, slot 12 in memory is going to be the register that contains the here, which is the next place that Forth is going to write to, and last is the header of the dictionary, of the last dictionary entry. So this is a dictionary entry. This is the header right here. So the header contains 4 byte links to the previous name, the previous entry, the previous header, in which case here is null. And then it contains 1 byte saying how many bytes are in the, or how many bytes are in the name, how many characters are in the name. Then it contains the name. And then it contains whatever the definition is. Okay. Yeah, I really don't know why it says 16 and 12 and 20. That doesn't make any sense. I don't know what AP stands for. I don't know what yeah, anyway, inc. This is div mod. This does a div and a mod, so it takes a number and divides it. It returns it takes a numerator and a denominator, and it returns the result of the division and the remainder. This does a little test to see if the number is between two numbers. So is x high and low? Is it between? And then the result is a copy of x and a flag. Kind of weird. Usually you would say, usually you would just keep the f back. Say do. And again, this doesn't have a, I didn't expose this in the dictionary, so it probably should be in the dictionary. That's -1. 0 not, right? Okay. Because there's not a to do, write a better, kind of up with a better way to write a negative number. All right, cursors. These are writes a value to address. Oh, a is the a pointer. So we have an a pointer and a z pointer, I guess. And I think the idea is that, sure. I think maybe this is what this is similar to the idea of ZW. So ZWrite, what we looked at in the assembler. I think this version, the self-hosting assembler targets the J version, and this is Pascal version. I think this is like a different take on that idea. Writing to. And same thing for the heap. The heap is all the part of RAM that you're writing. Here's the shell. This is the input buffer, so you can type up to 64 characters into this token buffer, and then when you execute the next word, so it's actually, as I type here, it's actually putting it into this buffer here. If I had exposed that as a name, I would actually be able to input that. Emit a space, emit CRLF, red, and black. Okay, so this prompt is actually, this prompt right here is actually written in the assembly language. Emit a space, okay, new line. Word by. Writes the word end in color. Okay, that's what. TA is a terminal attribute. Terminal right, something like that. Well, that is like temporary. Written as an opcode. Put S puts a string. Give an address of a counted string, so the strings are formatted as a count and a bunch of bytes. There's no marker there. Dictionary, entry name, that's what it is. So map an entry to its name, map an entry to its execution token, the address of the code. Yeah. Words, look at the last entry, read the integer, and then starting with the pointer to the last entry, read the name, print that as a string, and then on to the next. You see that's while this thing do end of loop, D and O are and then zap is to delete it. Dynamic call, this is what actually, oh, I see. So you load it into this address and then execute it? Yeah. Yeah, so at runtime, what you're going to do when you want to call one of these things from the shell is you're going to write to this address right here. And you can see it's a dynamic call is call, here's an address, and then you're going to return. So call, whatever this does, and then after it returns, then you return from this. And so it's a function that calls a function. So so load the name. That's kind of weird. Load the name, take the entry, given an entry. So you're looking at an entry on the stack, return its execution to return the address to jump to start executing. Load that integer. Oh no, sorry. Now that's on the stack, and then now we're gonna load the address to write it into, which is this address right here, and write it. And we're gonna write the integer. So we're gonna write this place into this part in RAM, and then we're gonna jump to, so it's self-modifying code here, right? So basically, whatever's on the stack, we write it to this address. We write the address that's on the stack. So you type the name in, it goes through the dictionary, it finds that name, finds out where that entry lives, and it writes it to the to this spot in memory, and then it calls this function right here, which in turn calls another function which has been rewritten dynamically. So it's self-modifying code has changed this thing, so you jump there, and that way we avoid the need for a dynamic jump operation. So we've implemented it ourselves. The virtual machine itself doesn't need to have something that says take some arbitrary value off the stack and use that as an address and jump to it, or take that arbitrary value and write to the instruction pointer or whatever. we've abstracted that away. We just do this, and so that's the magic there. Looks like I have a string compare. There really should be a loop page in here between the dictionary string compare. I'll make this a little bigger so the wrap so much. Oh, that's probably why. Excuse me. I don't like writing this low-level stuff. It's kind of tedious to write and hard to understand. So I want like a much higher level language, but this is bootstrapping, right? So that's what you got to do. I don't yet have a high level language that compiles to this, so I try to make the macro code look like this. So if over takes the second item on, so if you have ABC, it gives you AB, it gives you A, B, C, B. So it copies the B onto the, copies the second item on the stack. So basically, it's a way of like duplicating the second item on the stack rather than the top item, which is what DU does. Are these two things equal? So basically, duplicate the two items on the stack. Are they equal? If so, then so if the addresses are the same, return 1. But why does it say equal return? Oh, because yeah, that's a hack, right? These two things were equal. We made a copy of them because because the word equal consumes them. So now we consume the copies. We know they're equal, and now we need to get rid of them and put a 1 on the stack. Well, that's what equal does because we know they're equal. That's that returns. That's kind of a silly hack. And then so now we know that we have two unequal addresses on the stack, and we're going to copy the second one. We're going to read from that. We're going to duplicate it. This is tedious, right? I don't like doing this in my head. I don't like just stack juggling in my head. So I really want something that can visualize what's happening here and like step through this, like even as I'm explaining it. Because I think that's how it makes sense. Being able to step through it, which the debugger does, right? The debugger lets you do that. Anyway, so whatever, this sequence of instructions checks to see if the lengths are different, right? So they're this is enough to make that happen. And then now we start a loop. So F is a for loop. And .n is the next loop. Or is the keyword next that ends the for next. And basically we've so we check whether the pointers are the same. If they are, then we know they're the same. Then we check whether the lengths are the same, and if they're not, then we know they're not the same string, so it's not equal. So we do that same trick again. So we zap the result and then check again, and we get a 0 and return a 0. Now we're still here. We have two things of the same length, so we can just take whatever. We just take one copy of the length, and we have these two pointers that are the two pointers to the two strings, or the two strings where we're reading them. And we're going to increment one. We're going to swap it. We're going to increment the other one, and we can just keep swapping them back and forth. It doesn't matter which one is like. If we do encounter a difference, then we then we stop. So, but we can just keep swapping them back. If we, I guess at some point you might want to say, are these strings, less than or equal to each other? But that would be a different function. But anyway, the same kind of thing, and eventually we wind up returning a flag saying yes, they matched or they didn't. If you get all of the end. The way a .f works, it's a for loop, and basically you have a number on the stack. I think it gets pushed to the control stack. it's out of the way of your data, and it just it decrements that number until it reaches 0. So basically, if it's 0, then it does nothing. But either way, it records this address, pushes this on the stack, and then I think if it's 0, then it might not test for 0 cases, but in theory it should. And then the next says, well, okay, if the counter has reached 0, so decrement the counter if it's reached 0, then exit this loop or just continue running. But if it has not reached 0, then jump back up to the F. And of course, like, that's not what it means. What it means is emit the code that does that at runtime. But you can just treat it as if it's a language. All right, so word question mark. Attempt to find the word in the dictionary. Otherwise, this is the next string. Given a string, return an entry. It doesn't really explain what it does. I'm not going to worry about what it does when it's 0. It does something sensible. I guess we know what it does. Right? It says unknown word, right? Because it says unknown word. Oh, well, yeah. So it returns the entry 0 because you're just following the linked list, and when it reaches 0, then that's then you stop the loop, and that's what you return. 0 is the null pointer. Null pointer. All right, reading and writing numbers. This is so all numbers are in hex, I think. So FF. Oh, only in the assembler. In the assembler, you write FF, and it's by convention I write them 1 byte at a time. But so this is so you put 2 digits together and you write a byte. And you can write up to, in Forth you can have any base you want. Generally you switch between hex and decimal, right? So you have the string here and the logic is exactly the same, but you have to remember what the base is. And so the algorithm is the same, but this variable changes. So you just use 16 characters or 10 characters. You use 8 if you want, whatever you want. Whatever made sense to you. 7 if you want. Again, I'm just, I haven't looked at this code in 10 months, almost a year. And probably then it was. So anyway, this is a loop that takes a number on the stack and turns it into a bunch of digits that are printed out. Unknown word, there's the unknown word. Here's the unknown string, unknown, whatever digit. Is it a digit? Question mark. By number. Identifies the string as a number. And the point of that is that in this REPL, if you put in the number 234, so we're in decimal mode. Well, no, we're not. Yeah, we are. We're in decimal mode because it doesn't know what say 0003. Put in, it's going to. All right, local variables for alloc. Memory management, right? So this I worked through. I think it works. Here you can see we actually are defining a variable. So directly in this spot, read and write something at runtime. So we've got the, I don't know what U, S, and MP stand for. That should be, used size and previous. Right, so used is the actual length, S is the capacity, probably what it should be, and P is so it's a linked list of blocks. You have a size on each one. No, that can't be right. There are only 3 of them. It's not. This is not defining a structure. This is defining the head of this is defining 3 variables that are used in alloc. What end is. needed, round up to word and start. Used. MU is the used. S is size. P is a pointer. I don't know what the letter M stands. Memory used. Memory size and pointer. Anyway, yeah, this is a little memory allocation system. This will probably be a lesson in itself, and I'm going to have to refresh it. I mean, I have a rough idea what it's doing, but basically you're allocating variable size blocks. Very simple. I mean, it's not incredibly simple, but it's actually simple. And again, I wanted to visualize it. Then we have the REPL end token. I guess when you hit space, it triggers that. Here's the REPL. If at end of line, show prompt. New line. Read character from terminal. Oh, you can say backtick. There we go. Backtick brings up the debugger. That's neat. So the DB is a command in the machine itself knows as a debug interface. When you say continue, run. Now we're back here. It does not clear the screen for some reason. Okay. Yeah, so on space, echo a space, and then add a dummy character. And basically this right here is what's causing this to work. Not work, as in case maybe words. And then when we initialize, what is AP? P. A pointer to something, address pointer, a pointer. I don't know what that means. The AP to toke. I don't know. I don't know what AP means. They're both setting variables. I have to look at what AP does. Bug stuff. This should never execute, so trigger the debugger if we get here. Why should it never execute? Because of this if-then statement that's wrapping the entire function, or the entire code. So this is the end of that. That's the end of the BIOS. And then, what does it say? Huh. Oh, this is just printing out. This is what causes it to print out the word. When you first run, it prints out all the words. So this is what causes that. Like it's like the header here. And then, oh no, yeah. And then it launches the REPL. So this is defining everything that's in the BIOS, in the dictionary. So it's actually not big a deal. Like I think that's enough. This, the idea is you would do this in a couple passes, I think, and maybe have some like different little test programs at the bottom. Like define some functions and then test the functions and that kind of thing. I'm not sure. Like, I guess the test runner would have to. Basically, all that stuff I just looked at, I want to teach the concepts, make a little video about explaining how it works, and then challenge you, the student, to perform the task, to implement that function, to implement that piece of the BIOS. And so we want to break it into little chunks where it's like, 3 or 4 words per lesson, golf it to heck so that, we're not putting an undue strain on the user, on the student. And just basically teach you to do that each little step of the way. And plus, there's obviously some things missing because like we had a memory allocator, but we're not using it to allocate any memory, right? So this is not really a lesson yet. This was me going through and code, going through and writing what I thought the code ought to be to make this thing work, but I don't have any tests for them. So I think though that I probably do need tests for all these functions. So which probably also means first of all, like a version of this that does not use the color output. So like we have like a test BIOS and like a user interface BIOS. User interface would be like a text terminal, colors and all that. Whereas the testing interface is going to be much simpler because you don't parse a bunch of like garbage. Also, some of this is going to be done in the. There's going to be a version of the debugger that is going to be a computer-driven debugger. And that's what the test runner is really going to test. So some of this stuff, you're going to implement it in your own language, I think, in the host language, simply as a lesson to run these tests. And then at the end, you have a tool that basically is a debugger to help you write your own code. In the BIOS. So you write your own BIOS, write your own definition. Take this, modify it, do whatever. I have found, a lot of people have written little forths and put them out there, but it's like you need to see it grow. You need to see it grow from a small, like what I just did right here is not the way I wrote it. It's not the order I wrote it in. You got to start with like simple things, and like a very simple virtual machine that like again like in Tetris or LearnTris, you print out like the empty register, the empty state, the default state, and then you start assigning state, and then you check that you were successfully able to assign the state, and then it's the same. It's going to be the exact same pattern. Up until you start doing things, and then once you execute the instructions, it's so. Yeah. But, I'm just kind of thinking in my head, like some of the tests I want to write, like might involve the address of things that are you want it to be location independent, and most of the like the jump codes are location independent because you jump forward, backwards, up to. I think it's a short end. It reads a short end, so jump. You can jump forward up to 127 bytes, 128 bytes, backwards. I don't know what jump 0 does. I don't know. Maybe it just does nothing. Yeah, so you got a little tiny virtual machine. I want to be able to show this, something more than this debugger. You make it bigger. Again, so that like that what that's showing is a little slice of RAM, and if we move forward, you can kind of page through the RAM. and it's kind of showing you it knows how to read those little headers, and so it keeps a list of what the if you follow this format, it's able to guess what the addresses are, the things you're referencing. Right, but it's not showing you the name of the thing you're looking at. It's showing you the name of whatever. Oh, is this true? I don't know about to say. I was going to say like. Sure. Like, I'm not sure why there's so much empty spaces. These are registers. They're yellow because they're registers. This is blue because what? Input buffer? Is this meant to be the input buffer? I'm not sure. Yeah, I think code always execution always starts at 100. So the first 256 bytes are reserved. First, yeah, this would be 20. So the first 18, or sorry, the first 32 bytes are reserved as registers. And this, I don't remember what this is. It's just reserved space, I guess. The purple or the dark blue. And as you page through that, as soon as we get up to 100 or 100, which is 256x, now we're at the code here. We're at the start of the code that we're assembling. That's the LB0. And here's the jump 0 that's part of that. Load a byte 0, and then if it's 0, jump. It's unnecessary. That's hard coding the predicate, right? The 0, and then doing a conditional jump. But the assembler doesn't have another way to go to something that hasn't been defined yet. Right, you can't run a macro at the end of it to say go back and jump over everything. So it's a conditional jump with the condition. The condition is being hard coded to the number 0. Effectively, it's like saying if 0, basically. Anyways, so that's the actual code, and so now you can see the word here, HERE, and that's this is the bytes that are being compiled, and you can see that oh, I know what this is. Pink. Ah, yeah, these are being used for this cursor. No? Yes. Look at that. This number right here is changing. This number right here, as I move the cursor around, is changing. And if I go up, I don't know. So these flags, these registers are being used by the debugger. And I think this only has a limited amount of memory, like maybe 500 bytes of memory. Or no. It goes. The memory ends when the assembly runs. The rest is just unallocated space, I think. I don't know. I'll have to look at this again and clean this up a little bit. This is Pascal, and in Pascal I only have 16 colors to work with. The J version, I have a much nicer terminal library that has true color. Yeah, so there's just some predetermined size for what the RAM size is. All this is just empty space at the end. so I bet I can make a much nicer looking terminal. Okay. And that will have the benefit that I can run it in Godot as well, or at least render it in Godot. All right, well, I've been talking for 2 hours now, and maybe I didn't actually get to testing, but just to describe what I'm trying to do, and I kind of loaded some stuff in my head. So for those of you that popped in and out and were kind of listening to this, thanks for watching. And those of you watching on YouTube, thank you. There will be a much more coherent version of this in the weeks ahead, and much more detail. And this is going to turn into something process. Very messy. I need to talk things out sometimes. Find it interesting. I hope you'll stick around for the real thing. All right. Yeah. See you again soon. I don't know when. I'm still at my current job until the end of the year, and then it's the holidays, so it might be a little sparse. But January 1st, I'm going to be see my face on quite a bit more. Hopefully, a little more organized too. All right. Yeah. So thanks for watching.